Okay. Hello, engineering vibration students. We have a momentous occasion right now. We are launching into chapter 3. You are in for a treat. Okay, so what's different in chapter 3 is we are going from free vibrations to force vibrations. Specifically, not just any general force vibration, but it is force vibrations or harmonically excited force vibrations. So all of a sudden, we are adding an additional force to our system, okay? And we are going to go from mx double dot plus cx dot plus kx is equal to 0 to this new equation mx double dot plus cx dot plus kx is equal to f of t, where f of t is a magnitude force times some harmonic function. This could be sine omega t, or it could be f naught cosine omega t. Okay, but the important thing is that this force is harmonic. Okay, and it's varying with time in a harmonic manner. Okay, so what does that do to us? So let's start back with chapter 2, which we got really good at, and we're so good that we're bored and decided to make life more complicated. So under this system, remember we had a solution x of t is equal to the amplitude times its rate of decay, so negative zeta omega dt, times sine of omega, whoa there, Dr. Hilda, that's not omega dt. That's an omega nt. This is omega dt plus phi naught. It's going to be hard to do these without everybody here to find my typos. Okay. Now, and this is because life changes and it gets harder, we've gone from just x of t, and this is going to be called x underscore h. This is what's called the homogeneous solution, okay? And this is the solution when f of t is equal to 0 or when you're under free vibration, okay? So the homogeneous solution, x under subscript h, is the solution to your system when you were just to give it initial velocity or displacement and let it see what it does without any other external forces being applied other than the dampers, the mass, and the springs, okay? And remember, x of h, it technically depends upon time and your initial conditions, right? And that tells us that a is equal to the square root of v naught plus omega n zeta x naught squared plus x naught omega d squared over omega d squared, okay? And then, of course, phi naught is equal to tan negative 1 of x naught omega d over v naught plus omega n zeta x naught, okay? So a reason I wrote that out is to emphasize that, okay, this homogeneous solution, once again, it's the free vibration solution, so it depends upon the initial conditions, okay? Now we are going to introduce an additional complication where we have this forcing function, f of t, okay? And what that's going to do is that's, of course, going to change our solution. And what we're going to have now is we are going to have what's called, xp, which of t, which is going to be our particular solution, okay? And we'll find out through detailed study and fun that x of t is equal to f naught, which is the magnitude of the force, divided by k minus m omega squared and cosine omega t, okay? And does it have to be cosine or sine? It's fine. It doesn't change too much, okay? So let's talk about some of the things we got to focus on. When we just had c is equal to 0, right? When c was equal to 0, all we had was omega n. And then we made c greater than 0, and we added in omega n and omega d. And now we have this f of t, and this forcing function is at a straight up omega, okay? So the forcing function, there's no law of the universe that says it has to be at the you have to be forcing your system back and forth at damping frequency or natural frequency. You can be forcing it at any frequency you want. You know, the world's your oyster. So now we're going to end up with omega n, omega d's, and omega. And as we go along, you're going to have omega b's for beats and omega r's for the rotating imbalance. We're going to end up with a lot of omegas. So really make sure that you're paying attention to what omega you're putting where, because it really starts getting intense, okay, within the amount of omegas we have. Okay, so what do these x's of h's and p's look like, and what do they mean? Okay, so once again, x of h was equal to a e, I'm going to negative zeta omega nt sine omega dt plus phi naught, okay? xp is equal to f naught over k minus m omega squared times, I think the book uses cosine omega t, okay? So this homogeneous solution, and this is the particular solution, okay, the homogeneous solution, you'll see, as long as zeta is greater than 0, it's going to eventually decay out, okay? The particular solution, which depends upon the forcing function, it goes on forever, exactly the same, assuming your forcing function isn't changing, which we're not exactly ready to deal with that yet. Life's complicated enough, Dr. Hildreth. Now, your actual position, okay, your actual solution, and what's called the total solution, xt, is equal to the homogeneous solution. Let's make that a little neater. Xh of t plus the particular solution, okay? It's the principal superposition, okay? And what you can see is it's this solution right here in dashed added on top of the homogeneous solution, and then that's your solution. Eventually, this decays out and doesn't influence anything, and the particular solution takes over. You'll also see sometimes people refer this to steady state. Right, because if you make t time long enough, eventually this is what happens for your whole system. Okay. So once again, our position x of t now depends upon the initial conditions from the homogeneous solution, and then also the particular solution, okay, which is coming from our forcing function. Okay, so let's add a blank page below. And let's see where that comes from, okay? Okay, so let's focus first on the particular solution, okay? Or let's draw out a whole system. I'm going to do the derivation that the book doesn't do a particularly detailed job of. So we have mx double dot plus kx is equal to f of t, okay? So, sorry, I forgot to mention, I lied to you. I apologize. This is for c equal to 0. Sorry, there we go. This is for c equal to 0. Okay, I apologize for that. I forgot that. We start off in an undamped system. Well, we'll get to damped systems in section 3.8 or 3.4. Okay, so we're going to start off with our undamped system. Okay. And so for our undamped system, the homogeneous solution was equal to C1 cosine omega nt plus C2 sine omega nt. Remember, this is for C. There's no damping in our system. And this might look familiar. Remember, we went through, 4 or 5 different ways of representing this with e's and all cosines and all sines and exponentials and imaginaries. So we're going to follow the book's example, okay? And then we are going to assume the particular solution has the form of some magnitude of displacement times cosine omega t, okay? And then the velocity of the particular solution is equal to negative omega x sine omega t, and then the acceleration for the particular solution is negative omega squared x times cosine omega t, okay? Now, if we go and we plug this and this into here and here, what we end up with is negative m times negative omega squared x cosine omega t plus k times x cosine omega t is equal to f of t, which we had conveniently set equal to f naught cosine omega t. And once again, it doesn't matter if you call it cosine or sine, because you can always call your particular solution sine or cosine here. So the derivation is the same and the answer is the same. So our cosine omega t's all cancel out. So we have negative m omega squared x plus k x is equal to f naught, okay? And we can group our x's together, so that's k minus omega, keep that consistent, m omega squared times x, solve for x is equal to f naught times k minus m omega squared, okay? So now we have the particular solution equal to x cosine omega t, and we've solved for x, k minus m omega squared cosine omega t, okay? Now then, you're going to see the book introduce this term, delta st, and that is equal to what would be the static displacement due to this f naught. So if cosine omega t was just equal to 1, so omega was just equal, it's just always equal to 1, then you would have this static displacement is equal to f naught over k, right? That's how much it would displace. So they can say x is equal to f over k divided by k over k minus m omega squared over k. And I'm thinking, like, why would you do that? Well, remember that omega n is equal to the square root of k over m. So omega n squared is equal to k squared over m squared, okay? Oh, wait, there's no squares there, you silly goof. Is equal to k over m. So 1 over omega n squared is equal to m over k. And we could take this and put it in there, and we have x is equal to f over k over 1 minus omega over omega n squared, which is equal to the static displacement over 1 minus omega n squared. Okay, and I know what you're thinking. Why in Bob's name have you gone and just rewrote this thing, okay? And it's because there's a number of reasons. A, I want to make your life harder. No, I don't. Just kidding. I want your life to be as easy as reasonably possible. What we're going to do is now we're concerned more with this ratio of the driving frequency relative to the natural frequency, okay? Because that's going to tell us how big x is. So if omega, our driving frequency, exactly matched the natural frequency, well, then this will be 1, and 1 minus 1 is 0, and any number other than 0 divided by 0 is infinitely large. So now we're really kind of taking the things we care about in terms, and we can measure from our what is it called? Characteristic parameters, okay? And then you're also going to see the book do this thing where they'll say x divided by the static deflection, which I've also seen in other books as xk over f naught, sorry, it's an f naught, is equal to 1 minus omega over omega n squared. So they've normalized this, right? Because this is unitless, and that now is unitless. They'll normalize it, and they'll just graph how this function changes as a function of omega and omega n. In fact, let's see, I might even have that conveniently located here. Ho, ho, ho. Here's one of those cases where, once again, this is this x over dst, which once again is x over k and f naught, that dimensionless parameter. And here's r, which is omega over omega n. And what you can see is as you get close to 1, it goes infinitely large, and then as you go on the other side, it goes up from infinitely negatively large and then tapers off, okay? So I got a little ahead of myself because you know how it is. You can't help but get excited. Okay, so now we've derived that. So let's go and take a look at our total solution. Once again, this solution right here, does not include any initial conditions, okay? And those initial conditions are important to consider, especially for an undamped system, okay? So in this case, x total of t is equal to the homogeneous solution plus the particular solution, okay? Okay, and then our homogeneous solution is, here's one form of it, okay? And then here's the particular solution form, okay? So this ends up equaling C1 cosine omega nt plus C2 sine omega nt plus F naught over k minus m omega squared cosine omega t. Once again, this is omega. It's not omega n or omega d, it's omega, okay? And we're going to let x at t equals 0 to be equal to x naught, and x of dot of t equals 0 equal to x dot naught, okay? And this is the total and the total. Okay, so let's plug those in. So x total of t equals 0 is equal to x naught, which is equal to c1, and cosine of 0 is 1, okay? That's not even a what, I don't know what that is. 1, okay, plus c2 times 0, because sine of 0 is 0, plus f naught over k minus m omega squared times cosine of 0 is 1, okay? Now that tells us that x naught minus f over k minus m omega squared is equal to c1, okay? Okay, and there's our c1, so c1 equals that. Now let's put in our second boundary condition. X dot total at t equal to 0, okay? So to get that, we got to figure out what x dot is. So x dot of t is equal to, oh, it's going to be complicated. No, it's not going to be complicated. We got it. It's negative omega n c1 sine omega nt plus omega n c2 cosine omega nt, okay, minus f naught omega divided by k minus m omega squared times sine omega t, okay. So x dot of t, there's no 0, that's just x dot of t equal to 0 is now sine of 0 is 0, so we have negative omega n c1 times 0 plus omega n c2 times 1 minus f naught omega k minus m omega squared times 0. Okay, so we have, and that's all equal to x dot naught. So x dot naught is equal to omega n c2. That tells us that c2 is x dot naught over omega n, okay? So what do we see here, right? So our c2, if you go back to look at the derivations from before, hasn't changed. And our c1, instead of just being x naught, we also have this factor right here of this additional deflection that's going to occur in our system, okay? So now we can write our whole x of t is equal to x naught minus f over k minus m omega squared cosine omega nt plus x dot naught. Okay. Hold on. Well, I think I made I made a mistake in my notes. This is x dot naught over omega n. Yeah, I just made a mistake in my notes. Yeah, here we go. X dot naught over omega n cosine, whoa there, Nelly. Sine omega nt plus f naught over k minus m omega squared cosine omega t. Okay? Okay. And let's add in another blank page. Okay. Now then, the book introduces this thing called X, which is equal to, they call the maximum amplitude. Okay. This is really, should have a caveat. It's the maximum amplitude of the particular solution. Okay? You can, depending upon your initial conditions, have an amplitude larger. So here's an example where here, that right there is your x, because that's x of p. But once again, you can have amplitudes that are larger than that, right? Okay, so be very, very careful when you're doing your analysis, is a lot of times we're really interested in the steady state of the particular solution. But if you have things that are going to be stressed or anything like that, you do have to look at the maximum amplitude of your total solution. And we'll show you how to get that on another lecture. Okay? Let's make sure I'm not missing any important concepts here. Okay. Okay, so we already talked about this. This is just a neater version of what we had before. Okay. And once again, you'll see them have this parameter x k over f naught is equal to x over the static deflection, which is equal to 1 over 1 minus omega over omega n squared. Okay, and you'll see this called the amplitude ratio, or you'll see it called the magnification factor, and you also see it called the amplification factor. Okay, so they all mean the same thing. So now we get to remember 3 terms instead of just one. Okay, but really what it means is, okay, if you're for a given setup with k, here, let's use this pen, k and f naught, how big is your amplitude of your motion going to be, really based upon the frequency you're driving it at. Okay, now there's 3 cases that they talk about. Okay, case 1 is when omega over omega n is less than 1, right? So once again, x over dst, which is equal to x k over f naught is equal to 1 over 1 minus omega over omega n squared. Okay, so as long as this is less than 1, you're on this side of the curve. And what you can see is as you increase your frequency from 0, remember omega is your driving frequency, as you increase our driving frequency from 0 all up towards 1, we get essentially an infinite amplification factor, or amplitude ratio. Okay. Another thing that's important to notice is that when you have no driving frequency, omega is equal to 0, your displacement is equal to the static displacement. Okay. So when you're driving at less than the resonance, your amplitude will always be equal to or greater than their static deflection, okay? Then, as you pass through this point, we're going to get to case 2. Oh, another thing to remember is, I want to point out, is here's your driving force, and then here's your particular solution, and you'll notice that they are in phase. So they are in phase when omega is less than omega n, okay? But greater than 0, I guess. Okay? Now let's go to case 2. Okay, so case 2 is we're on the other side of that curve. So when omega is greater than, omega is greater than 1. Okay, in that case, we are on this side of the curve. Okay, there's a couple of things to notice. Okay. One is our phase is the opposite now. Okay, so you go through this transition, and our phase is the opposite for an undampened system. Undampened system doesn't exactly apply for a damped system. We'll see. Maybe it does. We'll see when we get to section 3.4. Okay, but the other thing that's important to notice is that right around here, okay, which I believe is square root of 2. I believe that's the square root of 2. Let's take a look. 2 square root. So right around, roughly around square root of 2. I'll have to go back and look at the notes, or we'll get there soon. Okay. The amplitude becomes less than the static deflection. So our amplitude ratio becomes less than 1. Okay, so what that means is if you drive it at higher frequencies, you would have less than the static deflection occurring, okay? Now this has a lot of important implications from a design perspective, okay? You have to, as a designer, decide, okay, do I want it the smallest amplitude of vibration I can get, so I should be driving at higher frequencies? But if I do drive it at a higher frequency, a frequency higher than the natural frequency, there will be some transient where I will go through the resonance frequency, and how long you stay there can impact, how much actual deflection you get, and the stresses you might cause in your system. Or is going through this resonance so harmful, or be there for so long, or so risky that I always have to be operating under here, okay? So we really, really, really care about this amplification factor, or amplitude ratio, because it dictates what our system response is going to be, both in steady state and also in transient, because, what we might think is a very short time, like a second, could be a really, really long time if your natural frequency is really high, right? Okay, so now we're going to start talking about the next few weeks. We're going to talk about design and designing our system, and what type of trade-offs we have to make to avoid this particular set of frequencies. Okay, that's case 1. That's case 2. Now, when we get to case 2, I am a little annoyed at the book. I'll tell you why. I think they make things more complicated than necessary. But next time I'll talk to them and tell them they should listen to me. So in the book, they now call xp of t is equal to negative x cosine omega t. Okay, so they put this negative sign in here, all so that they can call x is equal to dst, static displacement over omega n squared minus 1. Okay, well, isn't that fun? So that they're trying to do so that the amplification factor is positive. Okay, whatever. You guys have fun. It ends up being, like, if you take this negative and propagate it downward, it still is equal to dst over 1 minus, go to omega over omega n squared. Like, it's still the same thing. I'm sure there's some rationale, but for the life of me, I haven't figured it out. Okay, now we have this last case is when we're at resonance. Okay, so we have decided to lie right at resonance, but sometimes you might want to do, okay? A good example would be an ultrasonic welder. You're going to run it right around resonance. In this case, our x of t, okay, here's your initial conditions. This is your homogeneous solution, which doesn't care about driving, right? Now here's your particular solution right here. And this is, you'll notice that this term right here is still going to 0 and it's going to blow up, okay? And if you take the limit of this, you're going to end up with this term right here, okay? So here is your particular solution for when omega equals omega n. And what you're going to see is that over time, these ones, cosine and sine vary, but they don't change their amplitude. Okay, in this one, we have sine, but we also have this t outside of it. So this right here, this slope, this is dst omega nt over 2 is the slope of that, okay? And you can see it just takes off like nobody's business, okay? And that is kind of what happened to the Tacoma-Narrows Bridge, is it kept on vibrating more and more and more, because each cycle, more and more energy is effectively being put into the system, okay? And that is our response when omega over omega n equals 1, okay? Now, let's see, next page of notes. Okay. So we have case 1 and case 2, which are really the same. It's just a difference in phase. Okay. And then now we have our total response. Okay. And this is for, right, so this is our familiar homogeneous solution without damping. And then this is here's our particular solution, XH, and this is for omega over omega n less than 1. And then here it is for omega over omega n greater than 1. And what do we see? Okay, all that's changed is this sign of it, right? If you put this as plus, that becomes negative. It's the exact same equation, just written in a new way to make you have to memorize another equation. You don't. They are the same. Get over a book. Okay. So that's the total response of our system, right? So these are exactly the same. Okay. Okay. A couple more things we want to talk about is what's called the beading phenomena. And the beading phenomena occurs for any time that omega does not equal omega n, and I guess is greater than 0. It occurs, but it's most relevant when omega is kind of close to omega n. And what happens is, here's an example of, here is your driving frequency right here, okay? And laid on top of it is this natural frequency, okay? And they sum up together, okay? They're summing up together, okay? So if we were to arrange our solution, okay, which I haven't shown you. Why didn't I show them? Yeah, sorry friends, didn't show it to you. If we were to take these right here, if we were to take these, okay, right here, and do a little math, you would end up with this x of t, okay? It's the exact same thing, just with some extra math to rearrange things, okay? Okay. And now what you have is you have this long period, and superimposed upon it is the fast system, okay? And this is really important because now what do we see here? Okay, this is going to become our maximum displacement or amplitude. Okay, so there's our maximum amplitude. Okay. And then you'll see in the book, okay, that they've rearranged everything, because why not, where x of t is equal to, I'm going to rewrite it so you can write it with me, f naught over m over 2 epsilon omega sine epsilon t times sine omega t, okay? And epsilon, so omega b is equal to 2 epsilon, which is equal to omega n minus omega, okay? So epsilon is equal to omega b over 2, which is equal to omega n minus omega over 2, okay? So now x of t is equal to f naught over m divided by omega b times omega sine of omega b over 2 times sine omega of t. Okay? So there's your total, there's your system again, okay? Now, is that the homogeneous, the Beading phenomena? So this should all have a particular on them, xp of t. xp of t. xp of t. Thank you, book, for being lazy. That's, of course, the particular solution and doesn't include initial steady state. So what we see, okay, is we have, if we plot that, okay, this maximum displacement that it could ever possibly be is going to be f naught over m 2 epsilon omega, okay, or f naught over m omega b omega, okay, and then the frequency that this occurs at, okay, so you gotta go up and then down, okay, that is going to occur over a period tau b, okay, which is, of course, is equal to 2 pi over the beat frequency. Okay, so that was a lot of stuff that we've introduced, okay? So let's talk about the stuff we've introduced. We introduced a new set of equations of motion, plus kx is equal to f of t, okay? We've translated x of t into a total equaling the homogeneous solution plus the particular solution. That is when f of t is equal to 0. That depends upon initial conditions. And that is when f of t does not equal 0. And it does not depend upon initial conditions, okay? We have introduced f of t's form, okay? We have introduced a form for xp of t, and we introduced a bunch of them because, hey, why not? What else are you doing with your life, huh? Okay, so we have x of t is equal to x cosine omega t, where x is equal to x is equal to f naught over k over 1 minus omega over omega n squared, which is equal to f naught over k minus m omega squared, which is equal to the static displacement over omega n squared, okay? So that's one version of it, okay? We also introduced another form of x of t equaling f naught over m. I don't know why they put it there. I think it's just for scaling. E epsilon omega sine epsilon t sine omega t. Okay? And there we go. We introduced all sorts of wonderful phenomena. And let's make sure that I didn't miss anything. Oh, that's why. So, and when you read this section of the book for beading, I forgot one of my notes. This occurs for x, this particular solution is for x naught and velocity equal to 0. Whoa there, Nelly. So of course that means that our x homogeneous of t is equal to 0. That's why I was confused for a second. I knew I forgot to mention something. So this x is total, but it's really just a particular solution, okay? So we've introduced a bunch of new concepts. We've introduced new terms. Omega b is equal to omega minus omega n over 2, correct? Should be over 2, okay? Okay, and we started looking at systems that are near resonance, which is, so here's a system at resonance where the amplitude increases with all time, and then away from resonance. And what's important is once again, if you are below the natural frequency, your amplitude is static deflection and then increasing. If you're above that natural frequency, it can be infinitely large, and then it can even go less than the static deflection. Okay, that's all I wanted to talk about. I will see you online.